So here's something to think about as you're lying there, settling in for the night. Somewhere out in the universe, maybe everywhere in the universe, the fabric of space and time might be folded in ways that would let you step from one place to another without crossing the distance in between. Not science fiction, not fantasy. This is something that falls directly out of the most respected, most battle-tested equations in all of physics. The math says it's possible. The math has always said it's possible. And the story of how we figured that out, who figured it out, and what it actually means, that's what we're going to talk about tonight. No rush, nowhere to be, just you and me and the strangest tunnels that might or might not exist. Let's start at the beginning, and I mean the real beginning, not with wormholes themselves, but with the idea that space can curve at all, because that's the part you have to get comfortable with first. Before you can talk about a tunnel through space, you need to understand that space is the kind of thing that can have a tunnel in it. And that idea, the idea that space itself has a shape, that it bends and warps and stretches, that comes from one person, and you already know his name. Albert Einstein, 1915. He's 36 years old, living in Berlin, and he's just spent the most intellectually grueling decade of his life trying to generalize his theory of special relativity. Special relativity, from 1905, was the one that said, the speed of light is always the same, that time slows down when you move fast, that mass and energy are related by that famous equation. But special relativity only worked for things moving at constant speeds in straight lines. It didn't handle gravity. It didn't handle acceleration. And Einstein knew. He felt it in his bones, really, that gravity and acceleration were deeply connected. He had this beautiful thought experiment. Imagine you're standing in an elevator with no windows. If the elevator is sitting on the surface of the earth, you feel your weight pressing you into the floor. But if that same elevator were out in deep space, far from any planet, and a rocket were accelerating it upward at just the right rate, you'd feel exactly the same thing, exactly the same pull toward the floor. You couldn't tell the difference. No experiment you could do inside that elevator would reveal whether you were in a gravitational field or being accelerated. That's called the equivalence principle, and Einstein realized it meant something profound. Gravity isn't a force pulling on you. Gravity is the shape of space and time around massive objects. The Earth doesn't reach out and grab you. The Earth warps the geometry of the space around it, and you follow the most natural path through that curved geometry, which happens to lead you toward the ground. Now, to actually write this down as mathematics, Einstein needed a kind of math that barely existed at the time. He spent years struggling with tensor calculus, with differential geometry, with the mathematical language of curved surfaces and curved spaces. He collaborated with his old classmate Marcel Grossmann, who was a mathematician, and even Grossmann found it brutally difficult. There were false starts, wrong turns, published papers that Einstein later had to retract. At one point in 1913, he thought he had the final equations, and they were wrong. He spent 2 more years fixing them. And then, in November of 1915, he presented his field equations to the Prussian Academy of Sciences, and general relativity was born. Here's the thing about those equations. They're beautiful, but they're ferociously complicated. They relate the curvature of spacetime, how space and time are bent, to the distribution of matter and energy within that spacetime. Matter tells space how to curve, and curved space tells matter how to move. That's the famous summary, and it's a good one. But actually, solving those equations, Finding specific solutions that describe specific physical situations, that's extraordinarily hard. Einstein himself could only solve them approximately for simple cases. He could show that they predicted Mercury's orbital wobble correctly, which Newtonian gravity couldn't explain. He could show that light would bend around the sun, but exact solutions, clean closed-form solutions, those were a different challenge entirely. And this is where the wormhole story truly begins, because the very first person to find an exact solution to Einstein's field equations wasn't Einstein. It was a man named Carl Schwarzschild, and the circumstances of his discovery are one of the most remarkable stories in the history of physics. Carl Schwarzschild was a German astronomer and physicist, brilliant, widely respected, and in late 1915 he was serving in the German army on the Eastern Front, World War I. He was stationed in Russia, calculating artillery trajectories, because that's what you did with physicists during wartime. You put them to work on ballistics. He was also, at that point, already ill. He had developed a rare and painful autoimmune skin disease called pemphigus, which would eventually kill him. And somehow, in the middle of a war, suffering from a disease that was slowly destroying his body, Carl Schwarzschild got his hands on Einstein's newly published field equations and solved them. Not approximately. Exactly. He found the exact solution describing the curved spacetime around a perfectly spherical, non-rotating mass. He wrote it up and sent the paper to Einstein, who presented it to the Prussian Academy in January of 1916. Schwarzschild died just a few months later, in May of that year. He was 42. Think about that for a second. The first exact solution to the most important equations in gravitational physics was found by a dying man in a war zone. And that solution, the Schwarzschild solution, as it's called, contained something deeply strange, something that would take physicists decades to fully understand. The Schwarzschild solution describes how space and time curve around a massive object like a star, and it works beautifully for normal situations. It gives you the correct predictions for planetary orbits, for the bending of light, for gravitational time dilation. But the math also described something that happened at a particular distance from the center of the mass, a distance that depends on how much mass is there. At that distance, something in the equations went haywire. A term in the denominator went to zero, which meant certain quantities blew up to infinity. And at the very center, at the point where all the mass was concentrated, things got even worse. A true singularity, a point of infinite density and infinite curvature. Now, for an ordinary star like the Sun, that critical distance, what we now call the Schwarzschild radius, is deep inside the star itself. For the Sun, it's about 3 kilometers. The Sun's actual radius is nearly 700,000 kilometers, so the Schwarzschild radius is buried way down inside, in a region where the vacuum solution doesn't apply because there's matter in the way. So for normal stars, you never encounter the weird part of the solution. It's hidden. It's irrelevant. But what if a star were compressed, or compressed itself, down below its own Schwarzschild radius? What if all that mass were squeezed into a space smaller than that critical distance? Then the strange part of the solution would be exposed, out in the open, with nothing to hide behind. And that's a black hole. Though nobody called it that yet. Not for another 50 years. Here's what's really interesting for our purposes tonight. Physicists in the years after Schwarzschild's paper spent a lot of time trying to understand what that solution actually meant physically. What was happening at the Schwarzschild radius? Was it a real physical boundary, Or was it just an artifact of the particular coordinates Schwarzschild had used to write down his solution? Like how a map of the Earth has weird distortions at the poles that don't correspond to anything weird about the actual North Pole? And what about the singularity at the center? Was that real? Could nature actually produce a point of infinite density? These questions haunted physicists for decades, and in 1935, while wrestling with precisely these questions, Einstein himself, along with his colleague Nathan Rosen, stumbled onto something that would eventually become the concept we now call a wormhole. Einstein and Rosen were working at the Institute for Advanced Study in Princeton, New Jersey. Einstein had moved to the United States in 1933, fleeing the rise of the Nazis. Rosen was a young physicist, born in Brooklyn, who had become Einstein's research assistant. They were an interesting pair. Einstein, by then, the most famous scientist in the world, a cultural icon, 56 years old and increasingly skeptical of quantum mechanics, and Rosen, in his 20s, sharp and technically skilled. What they were trying to do was get rid of the singularity. Einstein hated singularities. He thought they were a sign that the theory was breaking down, that something had gone wrong with the mathematics. A point of infinite density isn't physical. It's a mathematical abstraction, and Einstein believed that a complete theory of physics shouldn't produce such things. So he and Rosen tried a mathematical trick. They took the Schwarzschild solution and performed a coordinate transformation. Essentially, they rewrote the same solution using different mathematical variables, and what they found was remarkable. Instead of a singularity, they got a bridge, a smooth, curved throat of spacetime connecting two separate regions. Imagine taking a sheet of paper, poking a hole in it, then taking another sheet of paper, poking a hole in that one too, and connecting the two holes with a short tube. That's roughly what the Einstein-Rosen bridge looked like in the mathematics. Two mouths, one throat, and a passage from one region of spacetime to another. Now, Einstein and Rosen didn't think of this as a tunnel you could travel through. That wasn't the point of their paper. They were trying to model elementary particles. They thought maybe an electron could be described as a tiny bridge in the geometry of spacetime, which would avoid the problem of point particles and their associated infinities. It was a creative idea, and it didn't really work out for that purpose. But the mathematical structure they described, the bridge, took on a life of its own. And here's the thing you should know. What Einstein and Rosen found in 1935 is not exactly what we mean today when we say wormhole. The Einstein-Rosen bridge, as originally described, has some serious problems if you want to think of it as a usable tunnel. For one thing, it's not stable. It forms and then pinches off so quickly that nothing, not even light, can make it through from one side to the other. It's like a bubble that inflates and pops faster than anything can cross it. So it's a bridge, but it's a bridge that collapses before you can set foot on it. But the idea was out there now. The idea that the equations of general relativity allowed for connections between different regions of spacetime, that the geometry of the universe might include shortcuts, passages, links between places that are otherwise enormously far apart. And once an idea like that enters physics, it doesn't go away. It gets poked at, extended, challenged, reimagined. The term wormhole itself didn't appear until 1957, more than 20 years after Einstein and Rosen's paper. It was coined by the American physicist John Archibald Wheeler, one of the great figures of 20th century physics. Wheeler had a gift for naming things. He's also the one who popularized the term black hole, though that came later, in 1967. Wheeler imagined spacetime at the very smallest scales, down at what's called the Planck length, about 10 to the minus 35 meters, so small that it makes an atom look like a galaxy. And he pictured it as a roiling, foaming, constantly shifting landscape of tiny connections and tunnels. He called it quantum foam, and the little tunnels threading through that foam, connecting one point to another, he called wormholes. The analogy was simple. Imagine a worm eating through an apple. If you're an ant walking along the surface of the apple, the shortest path from one side to the other is to go all the way around the curved surface, but the worm's tunnel cuts straight through the interior. A shortcut. Wheeler was a fascinating character, actually. Born in 1911 in Jacksonville, Florida, he got his PhD at 21, worked on the Manhattan Project, and spent decades at Princeton shaping the way physicists think about gravity, space-time, and quantum mechanics. He mentored Richard Feynman, for one thing, and he had this wonderful, almost poetic way of thinking about physics. He believed that the deepest truths about the universe would turn out to be simple and beautiful, and he spent his career looking for them. His phrase, "it from bit," captured his later belief that information might be more fundamental than matter itself. But in the 1950s, his focus was on what space-time looked like at its most extreme. And that's where wormholes entered the modern vocabulary. So by the late 1950s, the basic concept existed. General relativity allowed for bridge-like structures in spacetime. Einstein and Rosen had found them mathematically. Wheeler had given them a name and imagined them permeating the very fabric of reality at quantum scales. But nobody thought you could actually travel through one. The Einstein-Rosen bridge collapsed too fast. And besides, it existed inside a black hole, behind an event horizon, a one-way boundary that nothing could escape from. Even if the bridge didn't collapse, you'd have to fall into a black hole to reach it. And falling into a black hole was, to put it mildly, not survivable. So for about 3 decades, wormholes were a mathematical curiosity, a strange feature of the equations that physicists acknowledged but didn't take very seriously as something physical. They were like a grammatically correct sentence that doesn't mean anything. The math allowed it, but nature probably didn't. And then, in the mid-1980s, something unexpected happened. A science fiction novelist called up a physicist and asked a question that changed the entire field. The novelist was Carl Sagan, and the physicist was Kip Thorne, and the question was deceptively simple. If you wanted to send a character through space instantaneously, what would be the most scientifically plausible way to do it? And Thorne, instead of dismissing the question, took it seriously. He sat down with his graduate students and started calculating. And what they found was genuinely surprising. Because what Thorne and his students discovered was that general relativity didn't just allow for wormholes that collapsed instantly. It also allowed for wormholes that could, in principle, stay open. Wormholes you could actually travel through. And the paper they published in 1988 didn't just answer Carl Sagan's question. It essentially created a new subfield of physics. Let me back up just a little and set the scene, because the way this happened is such a perfect example of how science actually works sometimes. It's 1985. Carl Sagan is finishing his novel, Contact. You might know the movie with Jodie Foster, but the book came first. And in the story, his main character, Eleanor Arroway, needs to travel from Earth to the star Vega, which is about 26 light-years away. Sagan originally had her traveling through a black hole, which, sounds dramatic and science fiction-y. But Sagan was a real scientist, an astronomer, a planetary scientist, and he cared about getting the physics right. So he reached out to Kip Thorne at Caltech, who was one of the world's leading experts on general relativity, and essentially said, "Look, I want this to be plausible. What should I use instead of a black hole?" And Thorne could have just said, "Well, there's no known way to do it. Good luck with your novel." But he didn't. He was intrigued by the question. Because here's the thing about physicists, the good ones anyway. They love being asked impossible questions. It gives them permission to think about things they might not otherwise spend time on. And Thorne realized that the question, "Can you travel through a wormhole?" was actually a legitimate physics question that nobody had rigorously examined. People had assumed you couldn't, because the Einstein-Rosen bridge collapsed. But had anyone actually sat down and asked, okay, what would it take to keep one open? So Thorne brought the problem to two of his graduate students, Michael Morris and Ulvi Yurtsever, and they approached it in a really clever way. Instead of starting with a known solution to Einstein's equations and asking whether it contained a traversable wormhole, which is the usual approach, and which always gave you the collapsing bridge, they worked backwards. They said, let's start by describing what we want. We want a wormhole that a human being could travel through safely. No event horizons, no tidal forces that would rip you apart, no collapse. What does the geometry of space-time have to look like for that to work? And then, let's plug that geometry back into Einstein's equations and see what kind of matter or energy you'd need to create it. This is called a reverse engineering approach, and it's kind of beautiful in its logic. You're not asking what nature gives you. You're asking what you'd need to give nature to get what you want. And when they did the calculation, they got an answer. The geometry worked. You could write down a metric. That's the mathematical description of the shape of spacetime for a wormhole that was stable, traversable, and wouldn't kill you. The paper they published was called Wormholes in Spacetime and Their Use for Interstellar Travel, and it appeared in the American Journal of Physics in 1988. And it was a real, rigorous physics paper, not science fiction. The math checked out. But here's the catch. And this is where it gets really interesting, and also really weird. When Morris and Thorne looked at what Einstein's equations required to hold a wormhole open, they found that you'd need a very unusual kind of stuff, not ordinary matter, not even exotic matter in the way we usually think of it, like dark matter or antimatter. You'd need matter with negative energy density. Let me explain what that means, because it sounds impossible, and in some ways it kind of is, but in other ways, it's not as crazy as it sounds. Ordinary matter, everything you've ever touched, everything you've ever seen, has positive energy density. A cup of coffee, a rock, a star, even empty space filled with radiation, all positive. Positive energy density creates attractive gravity. It pulls things together. That's what curves space-time in the familiar way. The way that makes planets orbit stars and makes apples fall from trees. But to hold a wormhole open, you'd need matter that has the opposite gravitational effect. Matter that pushes space-time apart instead of pulling it together. Matter with negative energy density, which physicists sometimes call exotic matter. Now you might be thinking, that's it, game over. Negative energy doesn't exist. Wormholes are impossible. And honestly, that was a lot of people's first reaction. But here's what's wild. Negative energy density isn't entirely fictional. It actually shows up in quantum mechanics, in very specific situations. The most famous example is something called the Casimir effect, which was predicted by a Dutch physicist named Hendrik Casimir in 1948 and experimentally confirmed decades later. And the Casimir effect is strange and wonderful and worth understanding because it tells you something deep about the nature of empty space. Imagine you take two perfectly flat, uncharged metal plates and put them very close together in a vacuum. I mean really close. We're talking about gaps measured in nanometers, billionths of a meter. Now, according to quantum mechanics, empty space isn't really empty. It's seething with what physicists call vacuum fluctuations, tiny, temporary bursts of energy that pop into existence and vanish again almost instantly. Virtual particles, virtual photons, appearing and disappearing everywhere all the time. This is one of the strangest predictions of quantum field theory, and it's been confirmed by experiment over and over again. Here's the key. Outside the two plates, all wavelengths of these vacuum fluctuations can exist. There's no restriction, but between the plates, only certain wavelengths fit. It's like the difference between an open field, where any size of wave can propagate, and a narrow hallway where only certain standing waves can form. Think of how a guitar string can only vibrate at certain frequencies because it's fixed at both ends. The plates impose a similar constraint. So there are fewer vacuum fluctuations between the plates than outside them. And that means the energy density between the plates is actually lower than the energy density of empty space outside. And since we define the energy of empty space as zero, or at least as our baseline, the region between the plates effectively has negative energy density. The plates actually get pushed together by this imbalance. It's a real, measurable force, tiny but real. So negative energy density exists. It's a quantum phenomenon, and it occurs in incredibly small amounts under very specific conditions. But it exists. And that was enough for Thorne and his colleagues to say, look, the laws of physics don't categorically forbid the stuff you'd need to build a wormhole. It's not like we're asking for something that violates conservation of energy or breaks the speed of light in a vacuum. We're asking for something that quantum mechanics already tells us can happen, just on a much, much larger scale than we've ever seen. And that distinction matters. Because in physics, there's a huge difference between something that's forbidden by the laws of nature and something that's merely very, very difficult. Forbidden means it can't happen. Period. End of story. Very difficult means maybe, someday, somehow. And traversable wormholes fell into the second category. Now, how much exotic matter would you need? This is where the numbers get sobering. The original Morris Thorne wormhole required enormous amounts of negative energy. We're talking about quantities comparable to the mass energy of Jupiter, but negative. That's not something you can whip up in a laboratory. It's not something any civilization we can currently imagine could produce. But the calculation showed it was a matter of engineering, not a matter of principle. And over the years that followed, other physicists found ways to reduce the amount of exotic matter required. Matt Visser, a physicist who became one of the leading experts on wormhole physics, showed in the 1990s that you could design wormhole geometries that minimized the exotic matter, concentrating it in thin shells rather than filling the entire throat. The amount needed was still astronomical, but it was getting less astronomical with each new paper. And Sagan, by the way, got his answer. In the published version of Contact, Eleanor Arroway travels through a wormhole, not a black hole. And in the acknowledgments, Sagan thanked Kip Thorne for the physics consultation. It might be the only time a science fiction novel directly spawned a new area of serious physics research. But the 1988 paper opened up something much bigger than just a plot device. Because once you have a traversable wormhole, once you accept, even hypothetically, that such a thing could exist, you immediately run into a much more disturbing question. And Thorne and his students realize this almost right away. If a wormhole connects 2 points in space, could it also connect 2 points in time? Think about what that means. If you could manipulate a wormhole so that one mouth ages differently from the other, and special relativity tells us this is possible through the twin paradox, where a clock that travels fast runs slow relative to a stationary clock, then you could set up a situation where entering one mouth of the wormhole brings you out the other mouth at an earlier time. You'd have a time machine, not a science fiction time machine with blinking lights and a flux capacitor. A time machine that's consistent with the known laws of physics. Thorne, Morris, and Yurtsever published a follow-up paper in 1988 titled Wormholes, Time Machines, and the Weak Energy Condition, and it laid out exactly how this would work. Take a wormhole with 2 mouths, leave one mouth stationary, accelerate the other mouth to near the speed of light, then bring it back. Because of time dilation, the same effect that makes GPS satellites need their clocks adjusted. The traveling mouth has experienced less time than the stationary mouth. Now, the 2 mouths are at different points in time, even though they're connected through the wormhole throat. Step into one, come out the other, and you've traveled into the past. This was not a fringe idea published in an obscure journal. This was Kip Thorne, one of the most respected relativists in the world, publishing in Physical Review Letters, one of the most prestigious physics journals, and the reaction from the physics community was, to put it mildly, intense, because time travel doesn't just raise engineering questions, it raises logical ones, paradoxes. The most famous is the grandfather paradox. If you go back in time and prevent your own birth, then you were never born, so you never went back in time. So you didn't prevent your birth, so you were born, so you did go back. And round it goes. And this is where someone truly extraordinary enters the story. Someone who had been thinking about these questions longer and more deeply than almost anyone else alive. Stephen Hawking had been watching the wormhole discussion with great interest, and he had a very strong intuition about time machines. He didn't think nature would allow them, and in 1992, he proposed something he called the chronology protection conjecture. The idea that the laws of physics conspire to prevent time travel, even if individual equations seem to allow it. Hawking's argument was partly physical and partly philosophical. He pointed out that as you try to turn a wormhole into a time machine, quantum effects would build up. Vacuum fluctuations would pile up at the entrance to the wormhole, growing in energy, feeding back on themselves in a runaway loop until they either destroyed the wormhole or created conditions so extreme that our current theories break down. He famously quipped that the best evidence against time travel is that we haven't been visited by tourists from the future. But here's what's fascinating. Hawking couldn't prove the conjecture, not rigorously. The math got too hard at exactly the critical moment, right where quantum mechanics and general relativity collide, right where we'd need a theory of quantum gravity to know what really happens. And we don't have that theory yet. So the chronology protection conjecture remains exactly that, a conjecture. An educated guess by one of the most brilliant physicists who ever lived. And the question of whether wormholes could enable time travel remains genuinely open, which is a remarkable thing to be able to say about such a seemingly outlandish idea. Now, while Hawking was thinking about chronology protection, other physicists were digging deeper into the structure of wormholes themselves asking questions that would eventually connect to some of the most profound puzzles in all of physics. And the person who would make perhaps the most surprising connection of all was a theoretical physicist named Juan Maldacena, who in 1997 published a paper that would reshape our entire understanding of how gravity, quantum mechanics, and spacetime fit together. And to appreciate what Maldacena did, you need to know what he was working on, because it wasn't wormholes. Not directly. He was thinking about string theory. Now, string theory is one of those ideas that sounds almost too strange to take seriously, but it's been the dominant candidate for a theory of quantum gravity for decades. The basic idea, and I'll keep this gentle because it's late and this stuff can get dense, is that the fundamental building blocks of the universe aren't point-like particles. They're tiny, unimaginably tiny, vibrating strings of energy. Different vibrations give you different particles, the way different vibrations of a guitar string give you different notes. One vibration mode looks like an electron, another looks like a quark, another looks like a photon. And crucially, one vibration mode looks like a graviton, the hypothetical particle that carries the gravitational force. That's the magic trick. String theory naturally includes gravity, which is something that previous attempts to merge quantum mechanics and gravity had failed spectacularly to do. But string theory comes with baggage. It requires extra dimensions of space, not just the 3 we experience, but 9 or 10 spatial dimensions, depending on the version. The extra ones are supposedly curled up so small we can't detect them, and the theory is extraordinarily difficult to calculate with. For years, string theorists were making progress, but slowly, and often in very abstract mathematical territory that felt disconnected from anything you could test or observe. There was a sense in the mid-90s that the field needed a breakthrough, something concrete, something that would anchor all this beautiful mathematics to a physical picture people could actually work with. Juan Maldacena was a young Argentine physicist, barely 30 years old, working at Harvard. And in late 1997, he proposed something that electrified the entire theoretical physics community. It's called the ADS/CFT correspondence. And I know that sounds like alphabet soup, so let me unpack it slowly. Here's the setup. Imagine you have a universe, not our universe exactly, but a mathematically convenient one, that has a specific kind of curved geometry called anti-de Sitter space. Anti-de Sitter space is like a universe with a negative cosmological constant, which means it curves inward in a particular way. Think of it as a kind of saddle-shaped cosmos. It's not quite like the universe we live in. Our universe appears to have a positive cosmological constant, which is why it's expanding. But anti-de Sitter space is a beautiful mathematical playground because a lot of calculations become tractable there. Now, this anti-de Sitter space has a boundary. You can think of it like the interior of a sphere, where the boundary is the surface of that sphere. And what Maldacena proposed, and this is the part that made physicists' jaws drop, is that a theory of quantum gravity living inside this anti-de Sitter space is completely equivalent to a quantum field theory living on the boundary. Not approximately equivalent. Not sort of equivalent. Exactly. Perfectly. Mathematically equivalent. Two completely different looking theories, describing what seem like completely different physics, are secretly the same theory written in different languages. Let that sit for a moment. You have gravity, curved spacetime, black holes, maybe even wormholes, all happening in the interior, in the bulk, as physicists call it. And on the boundary, you have a quantum field theory with no gravity at all. Just particles and fields interacting on a flat surface. And these two descriptions contain exactly the same information. Anything you can calculate in one, you can calculate in the other. This is what physicists call a holographic duality, and the name is deliberate. Think about a hologram, a two-dimensional surface that encodes a three-dimensional image. Maldacena was saying something similar. The three-dimensional gravitational physics in the interior is encoded on the two-dimensional boundary. The boundary theory is like a hologram of the bulk. All the information about what's happening inside, including the geometry of spacetime itself, is somehow written on the surface. Now you might be thinking, okay, that's a beautiful mathematical relationship, but what does it have to do with wormholes? And the answer is everything. But it took about 15 years for people to figure that out. In the meantime, Maldacena's paper became the most cited paper in the history of high-energy physics. Thousands and thousands of citations. It opened up entirely new research programs. People who studied quantum field theory could suddenly say things about black holes. People who studied gravity could borrow tools from particle physics. It was a Rosetta Stone, translating between two languages that nobody had realized were describing the same reality. And one of the deepest puzzles it helped illuminate was the black hole information paradox. This is worth talking about because it connects directly to where the wormhole story goes next. Remember how Hawking showed that black holes radiate, that they emit what we now call Hawking radiation and slowly evaporate? Well, that discovery created an enormous problem. When a black hole forms, it swallows all kinds of stuff: stars, gas, information about every particle that fell in. Quantum mechanics says information can never be truly destroyed. It can be scrambled, encrypted, made practically impossible to recover, but it's always there in principle. It's baked into the mathematical structure of quantum theory, something called unitarity. But when a black hole evaporates via Hawking radiation, the radiation appears to be perfectly thermal, perfectly random, carrying no information about what fell in. It's as if the information just vanished. And that's a contradiction. Either quantum mechanics is wrong, or our understanding of black holes is incomplete, or something else very strange is going on. This paradox consumed theoretical physics for decades. Hawking himself initially argued that information really was lost, that black holes were special, that quantum mechanics needed to be modified. Most other physicists, including, notably, Leonard Susskind and Gerard de Hooft, disagreed. They believed information had to be preserved, that it somehow escaped in the Hawking radiation, even if we couldn't see how. The debate went back and forth for years, with Hawking and Susskind in particular developing something of a friendly intellectual rivalry over it. Susskind even wrote a book about it called The Black Hole War. And this is where ADS/CFT changed the game. Because in Maldacena's framework, the boundary theory is a perfectly ordinary quantum field theory, and quantum field theories are unitary. They don't lose information. Period. So if the boundary theory preserves information, and the boundary theory is equivalent to the bulk gravitational theory, then the bulk theory must preserve information too. Black holes can't destroy information. Maldacena's duality didn't explain the mechanism. It didn't tell you exactly how the information gets out, but it settled the question of whether it gets out. It does. It must. The mathematics demands it. Hawking eventually conceded in 2004 in a famous bet he'd made with John Preskill. He gave Preskill a baseball encyclopedia, the idea being that information is preserved. It was a gracious concession, and it was largely Maldaceno's work that made the case so compelling. But the how remained elusive. How does information escape a black hole? What's the mechanism? And this is where wormholes come roaring back into the picture in the most unexpected way. In 2013, Maldacena teamed up with Leonard Susskind, the very same Susskind who'd spent decades fighting Hawking over information loss. And they proposed something breathtaking. Their paper had one of the most elegant titles in physics: Cool Horizons for Entangled Black Holes. But the idea became known by a shorthand that's almost poetic in its simplicity: ER equals EPR. Let me explain what that means, because it's one of those ideas that, once you understand it, rearranges the furniture in your mind. ER stands for Einstein-Rosen, as in the Einstein-Rosen bridge, the wormhole we talked about earlier, the one from 1935. EPR stands for Einstein-Podolsky-Rosen, which refers to a different paper Einstein published that same year, 1935, about quantum entanglement. Think about that coincidence for a second. In the same year, Einstein co-authored two papers that seemed to be about completely different things. One was about a bridge connecting two regions of spacetime, a geometric, gravitational structure. The other was about the spooky connection between entangled quantum particles, two particles that share a quantum state such that measuring one instantly affects the other, no matter how far apart they are. Einstein actually hated entanglement. He called it spooky action at a distance and thought it proved quantum mechanics was incomplete. And now, 78 years later, Maldacena and Susskind were proposing that these two phenomena, wormholes and entanglement, are the same thing. Every pair of entangled particles is connected by a tiny wormhole. Every wormhole is a manifestation of quantum entanglement. The geometric connection through space-time and the quantum connection between particles are two descriptions of the same underlying reality. This is wild. Think about what it implies. Entanglement is everywhere in quantum mechanics. Every atom in your body is entangled with atoms it has interacted with in the past. And if ER equals EPR is right, then the fabric of space-time itself, the very geometry of the universe, might be stitched together by entanglement. Space might not be fundamental. It might emerge from quantum entanglement, the way temperature emerges from the motion of molecules. Temperature isn't a thing in itself. It's a description of what lots of molecules are doing collectively. And space-time might be similar, not a thing in itself, but a description of how quantum information is organized. Now, I should be careful here. ER equals EPR is a conjecture, not a proven theorem. It's an idea, a framework, a way of thinking. But it's an idea that has generated an enormous amount of productive research, and it keeps passing tests that people throw at it. When physicists work through specific examples in the ADS/CFT framework, particular configurations of entangled black holes, particular quantum states on the boundary, the geometry that shows up in the bulk is exactly what ER equals EPR predicts. Wormhole-like connections appear precisely when and where the entanglement structure says they should, and there's a beautiful philosophical dimension to this too. For decades, people thought of wormholes as exotic, speculative, almost science-fictional objects, things that might exist in principle, but probably don't exist in practice. And entanglement was considered strange but well-established, a thoroughly confirmed quantum phenomenon. If ER equals EPR is right, then wormholes aren't exotic at all. They're the most common things in the universe. They're just very, very small. Every entangled pair of particles is connected by one. You're full of them. The room you're in is full of them. They're just not the kind you could fly a spaceship through. But this raises a question that takes us even deeper. A question that was already simmering before Maldacena and Suskind wrote their paper, and it involves a thought experiment so disturbing that it nearly tore the theoretical physics community apart. It's called the firewall paradox, and it was proposed in 2012 by 4 physicists, Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully, who became known collectively by their initials, AMPS. And what they argued was that the very things physicists had taken for granted about black holes for decades couldn't all be true at the same time. And understanding why they said that, and why it caused such a storm, requires us to think carefully about what it actually means to fall into a black hole. So picture this. You're an astronaut. You've got a very good spacesuit and an adventurous streak, and you're falling feet first toward a large black hole. A really massive one, like the supermassive black holes at the centers of galaxies. And here's something that might surprise you. According to general relativity, crossing the event horizon should be completely uneventful. You wouldn't feel a thing. There's no wall, no barrier, no sign that says point of no return. The event horizon isn't a physical surface. It's a mathematical boundary, the radius beyond which light can no longer escape. But locally, right there where you're falling through, spacetime is smooth. The curvature is gentle, especially for a very large black hole. You'd look around and see nothing special. Your instruments would register nothing unusual. You'd just keep falling. This is called the no-drama condition, and for decades it was considered one of the foundational principles of black hole physics. An observer falling through the horizon should experience smooth, ordinary spacetime. No fireworks, no drama. Now, at the same time, physicists held 2 other principles to be sacred. One was unitarity, the idea that quantum mechanics preserves information. We talked about this, how Hawking's original argument suggested information was destroyed, and how ADS/CFT convinced most people that information must actually be preserved, that it comes out encoded in the Hawking radiation. The second principle was something called monogamy of entanglement. This is a deep property of quantum mechanics, and it says that if particle A is maximally entangled with particle B, then particle A cannot also be maximally entangled with particle C. Entanglement is exclusive. You can spread it around a little bit, share partial entanglement with multiple partners, but maximum entanglement is a one-to-one relationship. Think of it like a secret that can only truly be shared between 2 people. If you tell a third person, the original bond is diluted. Here's where the trouble starts. When a black hole emits Hawking radiation, each particle of radiation is created as part of an entangled pair. One particle escapes to infinity. That's the Hawking radiation we detect. The other falls into the black hole. So the outgoing particle is entangled with its partner behind the horizon. That entanglement across the horizon is exactly what makes the horizon smooth and drama-free for a falling observer. It's what guarantees that the quantum state at the horizon looks like ordinary vacuum, like empty space. If you disrupted that entanglement, the vacuum state would break down, and you'd get a burst of high-energy particles right at the horizon. A firewall. But here's the problem. If information is preserved, if unitarity holds, then after the black hole has been evaporating for a long time, more than half its original entropy has been radiated away. At that point, the new Hawking radiation being emitted must be entangled with the radiation that was emitted earlier. It has to be, because that's how the information gets out. The late radiation has to be correlated with the early radiation in very specific ways to encode the information about everything that fell in. So the outgoing particle is entangled with the early radiation. But we just said the outgoing particle also needs to be entangled with its partner behind the horizon to keep the horizon smooth. And monogamy of entanglement says it can't be maximally entangled with both. Something has to give. You can't have all three: smooth horizons, unitarity, and monogamy of entanglement. One of them has to be wrong. And AMPS argued that the thing most likely to go was the smooth horizon. Their conclusion was that old black holes, ones that have been evaporating for more than half their lifetime, don't have smooth event horizons at all. Instead, they have firewalls, curtains of extreme high-energy radiation right at the horizon that would incinerate anything falling through. Think about what that means. For decades, every physicist who studied general relativity was taught that the event horizon is locally indistinguishable from flat space. Einstein's equivalence principle, one of the cornerstones of general relativity, demands it. And AMPS was saying no, actually. Quantum mechanics forces the horizon to be a lethal barrier, a wall of fire. The reaction in the physics community was intense. This was 2012, and for the next several years, the firewall paradox consumed an enormous amount of attention. People took sides. Some argued that firewalls must be real, and we just had to accept that general relativity breaks down at the horizon. Others argued that there must be a subtle error in the AMPS reasoning. Others proposed radical alternatives. Maybe the interior of the black hole doesn't exist at all in the way we think it does. Maybe what we call the interior is actually encoded in the radiation outside, in some complicated way we don't yet understand. Joseph Polchinski, one of the four authors, was one of the most respected string theorists alive. He didn't propose the firewall paradox because he wanted firewalls to be real. He proposed it because the logic seemed airtight and he wanted the community to find the way out. He was essentially saying, here's a paradox, and the resolution, whatever it is, will teach us something profound about quantum gravity. Polchinski passed away in 2018, and the paradox remains one of his most impactful contributions. It forced people to think much more carefully about the interior of black holes and the nature of the event horizon. And this is where ER equals EPR enters the picture as a potential resolution. Remember what Maldacena and Susskind proposed, that entanglement and wormholes are the same thing. If the outgoing Hawking particle is entangled with the early radiation, then ER equals EPR says they're connected by a wormhole. And if the outgoing particle is entangled with its partner behind the horizon, that's also a wormhole connection, one that goes through the black hole interior. What Maldacena and Susskind suggested is that these aren't two competing entanglements. They're the same geometric connection, seen from different angles. The wormhole connecting the outgoing radiation to the early radiation, and the wormhole connecting it to the interior. They're all part of one complicated, multiply-connected spacetime geometry. Monogamy of entanglement isn't violated because the geometry rearranges itself in a way that accommodates all the connections simultaneously. Now, I want to be honest with you. This resolution is not universally accepted. It's elegant, it's compelling, and it passes a lot of consistency checks within ADS/CFT. But proving it rigorously requires a much better understanding of quantum gravity than we currently have. The firewall paradox is, in many ways, still open. Different groups of physicists have different opinions about what the correct resolution is. But what's remarkable is how the debate has shifted the conversation. Before the firewall paradox, Most physicists thought the event horizon was well understood. After AMPS, everyone agreed that the horizon is where the deepest mysteries of quantum gravity live. And wormholes, those strange speculative tunnels through spacetime that Einstein and Rosen wrote about back in 1935, turned out to be central to the story. Here's what's really lovely about this, if you step back and look at the arc. Wormholes started as mathematical curiosities, artifacts of Schwarzschild's solution that seemed physically meaningless. Then Wheeler gave them a name and imagined them as quantum foam. Then Thorne showed they could be traversable if you had exotic matter. Then Hawking worried they could become time machines. And now, in the 21st century, wormholes have become essential tools for understanding the deepest questions in physics, not as things you travel through, but as geometric manifestations of quantum entanglement, as bridges that stitch space-time together from the inside. And this shift in perspective opened the door to something even more surprising: the idea that you could actually study wormholes using quantum computers. Not build a wormhole in your garage. We're not there, and we may never be. But simulate the physics of a wormhole using a quantum system in the laboratory, and watch information behave exactly the way it would if it were traveling through a wormhole in anti-de Sitter space. And in 2022, a team of physicists claimed to have done exactly that, using one of Google's quantum processors. It was a headline that went around the world. Scientists create wormhole in the lab, and the reality, as usual, was more subtle and more interesting than the headline. The experiment was led by Maria Spyropoulou at Caltech, along with collaborators including Daniel Jafris and Alexander Zlokapa. And what they actually did requires us to understand one more beautiful piece of this puzzle, something called the SYK model, which stands for Sachdev-Yakitaev, named after Subir Sachdev, Jinwoo Ye, and Alexei Kitaev, and it's a quantum mechanical system that is about as simple as a model can be, while still capturing the essence of a gravitational system. And that's the key. The SYK model doesn't look like gravity on the surface. It's a bunch of particles, fermions specifically, and they interact with each other in random ways. Imagine you have a handful of quantum particles, and instead of each one interacting neatly with its nearest neighbor the way atoms do in a crystal, every particle is coupled to every other particle, and the strength of each coupling is chosen randomly. It sounds chaotic, and it is. That's actually the point. Because despite being this messy quantum mechanical system with no obvious geometry, no space, no distance between points, the SYK model, when you study its behavior at low energies, turns out to be mathematically equivalent to a theory of gravity in a nearly two-dimensional anti-de Sitter spacetime. It's one of the most concrete realizations of holography we have. A quantum system with no spatial dimensions at all, just particles interacting randomly, and yet its physics maps perfectly onto gravity in a curved spacetime one dimension higher. Kitaev was the one who really brought this into focus around 2015, building on earlier work by Sachdev and Ye from the 1990s. And the reason the SYK model became so important for the wormhole story is that it's simple enough, relatively speaking, to actually simulate on a quantum computer. You don't need millions of qubits. You don't need some impossibly complex setup. With a modest number of qubits and carefully designed quantum gates, you can create a system that behaves like the SYK model. And because the SYK model is holographically dual to gravity, the quantum information dynamics you observe in the lab should mirror what would happen to information falling through a wormhole. So here's what Spyropoulou's team actually did. They took Google's Sycamore quantum processor, the same family of processor that had made headlines in 2019 for Google's quantum supremacy claim, and they set up two coupled SYK systems on it. Think of it this way. In the holographic picture, one SYK system corresponds to one side of a wormhole, and the other SYK system corresponds to the other side. The coupling between them is like the wormhole throat connecting the two regions of spacetime. They injected a quantum state, a piece of quantum information, into one SYK system, let the system evolve, and then looked to see if that information appeared on the other side, in the second SYK system. And it did. The information scrambled, became seemingly lost in the quantum chaos of the first system, and then reassembled coherently on the other side. That pattern of scrambling and reassembly is exactly what you'd expect if information were traveling through a traversable wormhole. The quantum teleportation signature matched the gravitational prediction. Now, here's where it gets delicate and where the headlines got a little ahead of the physics. The team was careful, well, mostly careful, to say that they had observed dynamics consistent with wormhole teleportation in a holographic dual system. They did not create an actual wormhole in spacetime. No tunnel opened up in the lab at Caltech. What they showed was that a quantum system, when engineered to have the right properties, exhibits information transfer that is gravitationally interpretable as wormhole traversal. And that distinction matters enormously, but it's also genuinely profound. Because if holography is correct, if the boundary quantum system and the bulk gravitational system are truly two descriptions of the same physics, then in some deep sense, the wormhole is real. It's as real as anything else in the theory. The quantum system doesn't just resemble a wormhole. It is the wormhole, viewed from a different angle. But not everyone was convinced, and this is where the scientific community did what it does best, which is argue, loudly. Within days of the paper's publication in Nature in late 2022, critics pointed out that the team had to dramatically simplify the SYK model to fit it onto the available hardware. The full SYK model they wanted to study would have required far more qubits than Sycamore had available, so they used machine learning techniques to find a smaller, simplified version of the model, just 7 qubits on each side. That still preserved the key gravitational features. And some physicists, notably a group including Scott Aaronson and others, questioned whether the simplified model was really still in the regime where the gravitational interpretation holds. Was the wormhole-like behavior genuinely gravitational, or was it just generic quantum teleportation that you could get from any sufficiently scrambling quantum system? The distinction is subtle but important. Lots of quantum systems can transfer information from one subsystem to another. The question is whether this particular transfer had the specific signatures, the specific pattern of size winding, as the technical term goes, that distinguish gravitational wormhole dynamics from ordinary quantum chaos. The debate got heated enough that a follow-up paper by Jafferis and collaborators provided additional analysis defending the gravitational interpretation, while skeptics published their own analyses suggesting the simplified model was too stripped down to make strong claims. And honestly, as of now, the community hasn't fully settled this. It's one of those situations where the experiment was genuinely groundbreaking as a proof of concept. Nobody doubts that they successfully simulated a quantum system on a quantum computer and observed interesting dynamics. But the interpretation, the claim that this constitutes wormhole physics, remains contested, and that's okay. That's how science at the frontier works. You push into territory where the answers aren't clean yet. But here's what's really interesting about the bigger picture. Whether or not that specific 2022 experiment fully captured wormhole physics, the program it represents, using quantum computers to simulate quantum gravity is almost certainly the future of this field. We can't build particle accelerators powerful enough to probe the Planck scale, where quantum gravity effects become important. The energies required are roughly a quadrillion times higher than what the Large Hadron Collider can achieve. We're never going to directly observe quantum gravity through collisions, but if holography is right, we don't have to. We can study quantum gravity by studying quantum systems that are dual to gravitational theories. And quantum computers are the natural tools for simulating quantum systems, because they are quantum systems. A classical computer trying to simulate a quantum system with, say, 300 qubits would need more classical bits than there are atoms in the observable universe. A quantum computer with 300 qubits just is that system. It can simulate it natively. So, the vision that's emerging, and this is something people like Leonard Susskind and Patrick Hayden and Netta Engelhart and many others have been developing, is that quantum computers might become telescopes for spacetime. Not telescopes that look outward at distant stars, but telescopes that look inward into the quantum structure of spacetime itself. You build a quantum system in the lab, you engineer it to be holographically dual to some gravitational configuration, and then you study its behavior. You watch how information moves, how it scrambles, how it thermalizes, and from that behavior, you read off the geometry of the spacetime that the system is describing. If the information behaves a certain way, you know there's a wormhole in the dual description. If it behaves differently, maybe the wormhole has closed, or maybe the geometry has changed. And this connects to something we touched on earlier, the idea that entanglement builds geometry. Remember the ER equals EPR proposal, the idea that every pair of entangled particles is connected by a tiny wormhole. If that's true, then spacetime itself is stitched together by entanglement. Take away the entanglement, and spacetime falls apart. There's a beautiful result by Mark van Ramsdonk from around 2010, where he showed that if you take a holographic quantum system and gradually reduce the entanglement between two halves of it, the dual space-time geometry responds by developing a longer and longer bridge between two regions, a wormhole throat that stretches, until eventually, when the entanglement reaches zero, the space-time pinches off into two disconnected pieces. Entanglement is literally the glue that holds space together. Think about what that means. The space around you right now, the distance between you and the wall, between Earth and the Moon, between here and the Andromeda Galaxy, all of that spatial connectivity might exist because of quantum entanglement between the underlying microscopic degrees of freedom. It's not that entanglement happens in space, it's that space happens because of entanglement. The geometry is emergent. It comes from something deeper. And wormholes, in this picture, aren't exotic anomalies. They're the fundamental building blocks. Every connection in spacetime, every spatial relationship, is a wormhole of some kind, most of them too small and too quantum to notice, but collectively responsible for the smooth, continuous fabric of space that we experience at our human scale. It's Wheeler's quantum foam idea from the 1950s, but now with a precise mathematical framework behind it. Wheeler intuited that spacetime at the smallest scales would be a roiling mess of topology changes, wormholes flickering in and out of existence. He didn't have the tools to make that rigorous, but ADS/CFT and ER equals EPR are starting to provide those tools. Now, there's a catch, and it's a significant one. Almost everything I've described in the last few minutes applies specifically to anti-de Sitter space, That's the negatively curved spacetime where holography is best understood. And we don't live in anti-de Sitter space. Our universe, as best we can tell, has a small positive cosmological constant. It's closer to de Sitter space, a space-time that's expanding, that has a cosmological horizon, that behaves very differently from ADS in crucial ways. And extending holography from ADS to de Sitter space, to the kind of universe we actually inhabit, is one of the great unsolved problems in theoretical physics. People have been working on it for decades. There have been tantalizing hints, proposals like DS/CFT by Andrew Strominger, and more recent ideas involving what are called static patches and stretched horizons, but nothing as clean and well established as ADS/CFT. So when we talk about wormholes being the fabric of space-time, there's an asterisk. We know this works in anti-de Sitter space, and we strongly suspect something similar is true in our universe, but we can't prove it yet. The mathematical machinery that makes everything so elegant in ADS doesn't straightforwardly carry over. And this is where the field is right now. At this fascinating, slightly frustrating boundary between what we can demonstrate rigorously and what we believe must be true but can't yet show. And that brings us to one of the most ambitious ideas in all of modern physics, something that's been quietly gaining momentum over the last decade or so, and it goes by a deceptively simple name: the quantum error-correcting code picture of spacetime. The idea, developed primarily by Ahmed Almheri, Shidong, and Daniel Harlow in a landmark 2015 paper, is that the holographic dictionary, the mapping between the boundary quantum system and the bulk gravitational spacetime, works exactly like a quantum error-correcting code. And if you've ever wondered how your phone manages to send a text message through a noisy cellular network without the message getting garbled, you've already encountered the basic idea of error correction, just in a classical setting. But quantum error correction is stranger and more powerful, and the claim that spacetime itself is organized as a quantum error. Correcting code is one of those ideas that sounds so outlandish you almost want to laugh, until you see the math, and then you realize it explains things that nothing else can explain. And the connection to wormholes is deep and beautiful, so let's talk about it. Think about what error correction actually means in the everyday sense first. When you send a text message, the data gets broken into little packets, and each packet picks up noise along the way, interference from other signals, tiny voltage fluctuations in the electronics, all sorts of imperfections. If you just sent the raw data with no protection, by the time it arrived, bits would be flipped, characters would be wrong, and your message would be gibberish. So what engineers figured out decades ago is that you encode the information redundantly. You spread it out. Instead of storing one bit of information in one physical bit, you store it across many physical bits in a clever pattern, so that even if some of those physical bits get corrupted, you can still reconstruct the original information perfectly. The information isn't living in any single bit. It's distributed across the whole code in a way that makes it resilient. Now, quantum error correction takes this idea and makes it weirder, because in quantum mechanics, you can't just copy information. There's a theorem called the no-cloning theorem that says you literally cannot make a perfect copy of an unknown quantum state. So quantum error correction has to be more subtle. Instead of making copies, it encodes a quantum state into a larger system of entangled qubits, spreading the information across the entanglement structure itself. The information becomes, in a sense, non-local. It doesn't live in any particular qubit. It lives in the correlations between many qubits. And here's what Almhiri, Dong, and Harlow realized in 2015. This is exactly what the holographic principle is doing. Remember the basic setup of ADS/CFT. You have a boundary, a lower dimensional quantum system with no gravity, and it encodes everything about a higher dimensional bulk spacetime that does have gravity. The holographic dictionary tells you how to translate between the two descriptions, but the question that had been nagging people was, how exactly does this encoding work? If I point to a specific location deep inside the bulk spacetime, say, some point floating in the middle of anti-de Sitter space, which degrees of freedom on the boundary correspond to that point? And the answer turns out to be not just one region of the boundary. The information about that bulk point is encoded redundantly across large portions of the boundary in exactly the same way that a quantum error correcting code distributes information across many qubits. And this explains something that had been genuinely puzzling. In the holographic dictionary, there's a feature called subregion duality. If you take a patch of the boundary, not the whole thing, just a piece of it, that patch is supposed to describe a corresponding wedge-shaped region of the bulk. Different boundary patches describe different bulk wedges, but here's the thing, these wedges overlap. There are points in the bulk that are described by boundary region A and also by boundary region B, even though A and B might not overlap on the boundary at all. How can the same bulk point be reconstructed from two completely different sets of boundary data? It sounds contradictory, but if you think of it as an error-correcting code, it makes perfect sense. In a good quantum error-correcting code, the encoded information can be recovered from many different subsets of the physical qubits. Lose some qubits, and you can still reconstruct the original message from the remaining ones. That's the whole point of the code. Redundancy, resilience, the information being smeared out rather than localized. So spacetime, in this picture, is a code. The bulk geometry, the three-dimensional space you'd move through if you were a little creature living inside anti-de Sitter space, is the encoded message. The boundary quantum system is the physical hardware running the code. And the holographic dictionary is the encoding map. This is not a metaphor. Almhiri, Dong, and Harlow showed that the mathematical structure of the holographic mapping satisfies the precise technical conditions that define a quantum error-correcting code. Now you might be lying there thinking, okay, that's a cool way to think about it. But what does this have to do with wormholes? And this is where it gets really beautiful. Think about what happens when you have two entangled quantum systems, like the two boundary theories in the thermofield double state that we talked about earlier. The setup where Maldacena showed the dual geometry is an eternal black hole with an Einstein-Rosen bridge connecting two sides. Each boundary is running its own quantum error-correcting code, encoding its own bulk region. But because the two boundaries are entangled with each other, there's additional encoded information that doesn't belong to either side alone. It lives in the correlations between the two sides, and geometrically, that shared encoded information corresponds to the interior of the wormhole, the bridge connecting the two black holes. Let that sink in for a moment. The wormhole interior, the throat, the tunnel, whatever you want to call it, is literally the quantum information that's encoded in the entanglement between the two systems. It's not that the wormhole carries information, or that information travels through the wormhole. The wormhole is the information. It's the error-correcting code's way of geometrizing the entanglement structure. And this connects right back to ER equals EPR, but now with a much more precise mathematical framework. The Einstein-Rosen bridge is the geometric manifestation of the quantum error-correcting code that encodes the shared entanglement between two systems. And here's where things get even more interesting, because this picture has practical consequences, or at least consequences that physicists can calculate and check. One of the most important results that came out of this line of thinking involves something called the Ryu-Takayanagi formula, which was originally proposed by Shinsei Ryu and Tadashi Takayanagi back in 2006. Their formula gives you a way to calculate entanglement entropy, a measure of how entangled two quantum systems are, using geometry. Specifically, if you want to know how entangled a region of the boundary is with the rest of the boundary, you find the minimal surface in the bulk that separates the corresponding bulk region from everything else, and the area of that surface, measured in Planck units, gives you the entanglement entropy. It's like the Bekenstein-Hawking formula for black hole entropy, but generalized to any region, not just black hole horizons. The Ryu-Takayanagi formula was already one of the most important results in theoretical physics in the last 20 years, but the error-correcting code picture explained why it works. The minimal surface is essentially the boundary of the code's causal wedge. It marks the transition between what can be reconstructed from a given boundary region and what can't. The area of that surface counts the number of encoded degrees of freedom that are at risk, so to speak, the ones that sit right at the edge of what the code can protect. And when you apply this to wormhole geometries, the minimal surface threads through the wormhole throat, and its area tells you about the entanglement holding the wormhole open. There's a beautiful refinement of this that came along in 2014 and 2015, developed by several groups, including Engelhardt and Wall, called the quantum extremal surface prescription. It generalizes the Ryu-Takayanagi formula to include quantum corrections, not just the area of the surface, but also the entanglement of quantum fields across the surface. And this refined version turned out to be exactly what was needed to resolve the black hole information paradox in a precise, calculable way. In 2019, a series of landmark papers by Pennington and independently by Almhiri, Engelhardt, Marolf, and Maxfield used the quantum extremal surface formula to compute the entropy of Hawking radiation over the full lifetime of an evaporating black hole, and they got the right answer. The entropy follows what's called the Page curve, named after Don Page, who predicted its shape back in 1993. The entropy rises as the black hole emits radiation, reaches a maximum around the halfway point of evaporation, and then decreases back to zero as the black hole finishes evaporating. This is exactly what you'd expect if information is preserved. If the radiation starts out looking random, but gradually becomes more and more correlated, eventually encoding everything that fell into the black hole. And here's the kicker. The key geometric ingredient that makes the Page curve come out right is a new kind of surface, a quantum extremal surface that passes through the interior of the black hole. And in the calculations, this surface can be understood as a kind of wormhole. Specifically, in the replica trick calculations that underpin the derivation, you sum over geometries that include connections between different copies of the spacetime. And these connections are wormholes. They're sometimes called replica wormholes, and they contribute to the gravitational path integral in a way that was previously overlooked. Without them, you get the wrong answer. The entropy just keeps rising forever, which would mean information is destroyed. With them, you get the Page curve. Information is preserved. So wormholes saved unitarity. Wormholes, those things that started as a mathematical curiosity in Einstein and Rosen's 1935 paper that Wheeler played with in the 50s, that Thorne made traversable in the 80s, turned out to be the missing ingredient in one of the deepest problems in all of physics. The black hole information paradox, which had tormented the field for nearly 50 years, was resolved by taking wormholes seriously as contributions to the quantum gravitational path integral. Now, I want to be careful here, because resolved is a strong word, and not everyone in the field would use it. What these calculations showed is that within the framework of semi-classical gravity treated approximately with quantum corrections, the Page curve comes out right. But there are still deep questions about what this means for the full theory of quantum gravity, whatever that turns out to be. The replica wormholes are saddle points in a gravitational path integral, and we don't fully understand what that path integral means, or whether it's the right way to think about quantum gravity beyond approximation. There are researchers who think the replica wormhole story is pointing us towards something profound and correct, and others who worry that we're reading too much into a calculation that might not survive in the exact theory. But even the skeptics tend to agree that something important happened in 2019. The convergence of ideas, holography, error correction, entanglement entropy, extremal surfaces, wormholes, all clicking together to produce the Page curve, felt like a genuine breakthrough. And it all traces back, in one way or another, to taking seriously the idea that space-time geometry emerges from quantum entanglement, and that wormholes are the geometric signature of that entanglement. So where does this leave us? We've come an enormous distance from Einstein-Rosen's bridge, haven't we? What started as a mathematical feature of the Schwarzschild solution, a curiosity really, something that most physicists dismissed as physically irrelevant, has become central to our deepest understanding of quantum gravity. Wormholes aren't just tunnels through space. They're the stitching that holds space-time together. They're the error-correcting code that makes the holographic principle work. They're the geometric face of entanglement, and they might be the key to understanding how black holes process and release information. But there's a question we haven't really addressed yet, and it's the one that probably brought you here in the first place, the one that science fiction has been asking for over a century. Could we ever actually travel through one? Could a wormhole ever be a real physical thing that a person or a spacecraft could use? And the honest answer is complicated and fascinating, and it involves some of the most recent work in the field, ideas that are being developed right now as we speak by people who are pushing the boundaries of what we understand about the laws of physics. So let's talk about it. Let's talk about whether wormholes could ever be real, physical, traversable things. And the place to start, honestly, is back with Kip Thorne, because he was the one who really cracked open this question in a serious way. Remember, back in 1988, Thorne and his collaborators, Mike Morris and Ulvi Yurtsever, published that paper showing that a traversable wormhole was at least consistent with general relativity, provided you had exotic matter with negative energy density. And for a long time, that requirement seemed like a deal breaker. Negative energy density sounded like science fiction. It sounded like you were just wishing for something impossible and then building your theory around the wish. But here's the thing. Negative energy isn't quite as impossible as it sounds. Quantum mechanics actually allows for it in certain situations. The Casimir effect, for instance. If you take two perfectly flat, uncharged metal plates and bring them very close together in a vacuum, we're talking microscopic distances, the quantum vacuum between them has less energy than the quantum vacuum outside them. The energy density between the plates is effectively negative. It's a tiny effect, almost absurdly tiny, but it's real. It's been measured. So negative energy isn't forbidden by the laws of physics. It's just incredibly hard to produce in any useful quantity. And the amount you'd need for a human traversable wormhole in the classic Morris Thorne sense is staggering. We're talking about quantities of negative energy comparable to the mass energy of Jupiter, or in some configurations, comparable to stellar masses, all concentrated in a thin shell around the wormhole throat. That's not something any conceivable technology could produce. So for decades, the practical answer was, sure, the equations allow it, but the engineering is so far beyond anything we could ever do that it's essentially impossible. But then something interesting started happening. Physicists began asking a more subtle question. Instead of asking, can we build a wormhole big enough for a person? They started asking, can we build a traversable wormhole at all, even a tiny one, even in principle, without needing exotic matter that we have to put in by hand? And this is where the story connects back to everything we've been talking about. The holographic principle, ADS/CFT, entanglement, all of it. In 2017, Ping Gao, Daniel Lewis Jafferis, and Aaron Wall published a really remarkable paper. What they showed was that if you have two black holes that are entangled, connected by an Einstein-Rosen bridge, just like in the ER equals EPR picture, and you allow a very specific kind of interaction between the two boundary systems in ADS/CFT, then the wormhole connecting those two black holes can become traversable. A particle, or a signal, could actually pass from one black hole through the bridge and emerge from the other. Now let's slow down and think about what that means, because it's genuinely wild. The interaction they described is sometimes called a double trace coupling. Think of it this way. You have two copies of a quantum system living on two separate boundaries, Alice's boundary and Bob's boundary. These two systems are entangled. There's a wormhole in the bulk connecting them. Normally, that wormhole is not traversable. It pinches off too quickly for anything to get through, just like the old Einstein-Rosen bridge. But Gao, Jafferis, and Wall showed that if Alice measures some of her qubits and sends the results to Bob through an ordinary classical channel, just regular communication, nothing exotic, and Bob then applies specific operations to his qubits based on Alice's message, this creates a tiny burst of negative energy inside the wormhole. Not negative energy that you had to manufacture and inject. Negative energy that arises naturally from the quantum correlations between the two systems, activated by this particular protocol. And that burst of negative energy is just enough to prop the wormhole open for a brief moment, long enough for a quantum of information to pass through. Think about what that means for a second. The exotic matter problem, the thing that seemed like an absolute barrier to traversable wormholes, gets sidestepped. You don't need Jupiter masses of negative energy. You need quantum entanglement and a clever communication protocol. The negative energy emerges from the structure of the entanglement itself. Now, you might be thinking, wait, Alice has to send Bob a message through ordinary space for this to work? Doesn't that defeat the purpose? If you need to send a regular message anyway, why bother with the wormhole? And that's a fair question. The answer is that the information that travels through the wormhole is not the same as the classical message Alice sends Bob. The classical message is like a key that unlocks the wormhole. The actual quantum information, the qubit that falls into Alice's black hole, travels through the bulk, through the wormhole geometry, and pops out of Bob's black hole. And it arrives in a way that's deeply connected to quantum teleportation, the protocol that Charles Bennett and colleagues described back in 1993. In quantum teleportation, you use a shared entangled pair and two bits of classical communication to transfer a quantum state from one place to another. What Gao, Jafferis, and Wall showed is that when you do quantum teleportation in a holographic system, the bulk description of that process is literally a particle traveling through a wormhole. Let that sink in. Quantum teleportation, which we already know how to do in the lab, we've been doing it since the late 1990s, has a gravitational dual description. And that description is traversal of a wormhole. The two pictures are the same phenomenon seen from different sides of the holographic dictionary. This was the theoretical backbone behind the Sycamore experiment we talked about earlier, the one by Spiropoulos' team in 2022. They weren't creating a wormhole in real space. They were implementing this teleportation protocol in a holographic quantum system, the SYK model, and showing that the pattern of information transfer matched what you'd expect if a wormhole were the geometric description of what was happening. The traversable wormhole on a quantum computer headline made people argue about whether it was really a wormhole, and honestly, the answer depends on how seriously you take the holographic dictionary. If holography is right, if the boundary quantum mechanics and the bulk geometry are truly equivalent descriptions of the same physics, then yes, quantum teleportation in a holographic system really is wormhole traversal. They're not analogies for each other. They're the same thing described in two different languages. But let's come back to the question of whether you could ever have a macroscopic, science fiction-style wormhole, something you could fly a spaceship through. And here the news is, well, it's mixed, but it's more interesting than you might expect. In 2019, Juan Maldacena and Alexei Milikin, and separately Ping Gao and a few others, explored a fascinating possibility. They looked at wormholes in a universe with specific properties, extra dimensions, particular kinds of matter fields, a particular cosmological setup, and found solutions where a traversable wormhole could exist that was large enough for a human to pass through. The Maldacena-Milekin wormhole, in particular, uses the Casimir energy of massless fermion fields wrapping around extra compact dimensions to provide the negative energy needed to keep the throat open. The extra dimensions are doing the heavy lifting. The negative energy isn't something you have to manufacture. It arises from the topology of the extra dimensions themselves. Here's the kicker, though. From the outside, these wormholes would look almost indistinguishable from black holes. They'd be tiny. The mouth might be only a few fractions of a millimeter across, even though the interior geometry could be enormous. And the trip through would be long. Not long in the sense of distance, but long in terms of time as experienced by someone outside. From the traveler's perspective, the journey might take a fraction of a second. But from the perspective of someone watching from outside, the trip could take 10,000 years or more. So it's traversable, technically, but it's not exactly practical for commuting. And there's another catch. These solutions require very specific conditions, particular numbers of fermion species, particular sizes for the extra dimensions, that may or may not match our actual universe. We don't know whether our universe has the right ingredients. String theory suggests extra dimensions exist, but we haven't confirmed their size or topology. So these wormhole solutions are proof of concept results. They show that the laws of physics, as we currently understand them, don't absolutely forbid macroscopic traversable wormholes. But they don't tell us that such things exist in our universe. There's been other work too. In 2021, Jose Blasquez Salcedo, Christian Knoll, and Eugen Radu found traversable wormhole solutions in a theory with a particular kind of coupling between a scalar field and the Gauss-Bonnet term, a higher curvature correction to general relativity that string theory predicts should exist. These wormholes don't need exotic matter at all in the traditional sense. the higher curvature terms in the gravitational action effectively do the job that exotic matter would normally do. The catch is that these wormholes are small, Planck scale or near it, and we don't know whether the specific theory they used accurately describes our universe at those scales. So here's where things stand, as honestly as I can put it. We know that the equations of general relativity allow wormholes. We know that quantum effects can produce the negative energy needed to make them traversable, at least in principle. We know that in holographic theories, traversable wormholes arise naturally from quantum teleportation between entangled systems. We know that in certain theoretical setups with extra dimensions or higher curvature gravity, macroscopic traversable wormholes are possible without violating any known laws of physics. But we don't know whether our specific universe, with its specific particle content, its specific number and topology of extra dimensions, its specific cosmological history, actually permits them. And there's one more thing worth mentioning, something that brings us full circle in a beautiful way. Remember Hawking's chronology protection conjecture? The idea that the laws of physics conspire to prevent time travel? Well, traversable wormholes are intimately connected to this, because if you could create a traversable wormhole and then accelerate one mouth relative to the other, using special relativistic time dilation, you could in principle turn it into a time machine. One mouth ages slower than the other, and suddenly the wormhole connects two different times as well as two different places. Hawking argued that quantum effects would destroy any wormhole before it could be turned into a time machine. And most physicists still think something like that is probably true. But the precise mechanism, exactly how and why nature prevents it, remains an open question. Some recent work suggests that the same quantum effects that make wormholes traversable also impose limits on how much information can pass through, and how the wormhole responds to attempts to create closed time-like curves. The wormhole, in a sense, might protect itself, and this connects to something even deeper, something that the theorists working on quantum gravity are only beginning to understand. It has to do with the nature of space-time itself at the most fundamental level, and with a question that might sound almost philosophical, but turns out to be deeply physical. Is space-time fundamental? Or is it something that emerges from a deeper layer of reality? That question, that strange, almost unsettling question, is where all of these threads we've been following finally converge. Think about it this way. Throughout this whole journey, we've watched the concept of a wormhole evolve. It started as a mathematical curiosity, a bridge in the geometry of spacetime that Einstein and Rosen noticed in 1935. Then Wheeler gave it a name and imagined quantum foam full of tiny ones. Then Thorne showed that traversable ones were at least conceivable if you had exotic matter. Then Maldacena and Susskind proposed ER equals EPR, and suddenly wormholes weren't just tunnels through space. They were entanglement made geometric. Van Ramsdonk showed that if you removed entanglement, space-time itself fell apart. Almhiri, Dong, and Harlow revealed that the holographic dictionary works like a quantum error-correcting code, with the geometry of the bulk emerging from the entanglement structure of the boundary, and the replica wormholes that solved the page curve. Those weren't wormholes you could fly a spaceship through. They were contributions to a mathematical path integral, saddle points in a sum over geometries, and yet they gave physically correct answers about information and unitarity. So here's the thing. Every one of these discoveries points in the same direction. Space-time, the fabric of the universe, the stage on which everything happens, the thing Einstein spent his life describing with such beautiful precision. Space-time might not be the bottom layer. It might be woven from something else, something more fundamental. And the thread it's woven from appears to be quantum information. Entanglement, the correlations between quantum systems. Now, that's a wild claim. Let's sit with it for a moment, because it deserves some care. When you learned about space-time in school, or maybe just absorbed it from popular science, you probably got the picture that space-time is the arena. It's the container. Things happen in space-time. Particles move through it, fields vibrate in it, gravity curves it. Even in general relativity, where space-time is dynamic and bends and warps, it's still the fundamental thing. The metric tensor, that mathematical object that tells you the distance between any two nearby points, is the basic variable of the theory. Everything else is built on top of it. But what if the metric tensor isn't fundamental? What if it's derived? What if there's a deeper description of reality that doesn't use space-time at all, and space-time only shows up as a kind of large-scale approximation, the way temperature shows up when you zoom out from the jittering of individual molecules? Temperature isn't a fundamental property of a single molecule. It's a collective phenomenon. It emerges from the statistics of many molecules interacting. And there's a growing body of evidence suggesting that space-time might be exactly like that. Not fundamental, emergent. This idea has a name, or at least a slogan, "It from Qubit." The phrase was coined by John Wheeler, actually, the same Wheeler who named the wormhole. Wheeler spent the last decades of his life obsessed with the idea that information might be the bedrock of physics. He wrote about it in the early 1990s, and at the time it seemed almost mystical, more philosophy than physics. But the work we've been talking about, a DS/CFT, ER equals EPR, quantum error correction in holography, the page curve, all of it has given Wheeler's intuition mathematical teeth. Here's how the picture works, at least in the best understood cases. In the ADS/CFT correspondence, you have a quantum theory on the boundary. No gravity, no space-time curvature, just quantum fields interacting on a fixed, lower dimensional space. And from the entanglement structure of that quantum theory, an entire extra dimension of space emerges. The bulk, the interior, the place where gravity lives. The Ryu-Takayanagi formula tells you that the area of a surface in the bulk equals the entanglement entropy of a region on the boundary. So the geometry of the interior is literally encoding the entanglement of the exterior. Change the entanglement, change the geometry. Remove the entanglement, and as Van Ramsdonk showed, the geometry disconnects. The space falls apart. And wormholes are the most dramatic example of this. Two entangled black holes on the boundary correspond to a connected geometry, a wormhole, in the bulk. The entanglement is the wormhole. The wormhole is the entanglement. They're not analogous. They're not metaphorically related. In the context of ADS/CFT, they are literally two descriptions of the same thing. So if you're lying there thinking, wait, does that mean every pair of entangled particles is connected by a tiny wormhole? Well, that's exactly what ER equals EPR suggests. Maldacena and Susskind proposed that even ordinary entanglement between two electrons might correspond to some kind of ultra-microscopic, highly quantum wormhole. Not a smooth tunnel you could draw a picture of, but a quantum gravitational connection between 2 points in spacetime. It's a conjecture. It's unproven. But it's consistent with everything we know, and it's one of the most beautiful unifying ideas in modern theoretical physics. It says that the two great pillars of quantum weirdness, entanglement and the geometry of spacetime, are secretly the same phenomenon viewed from different angles. Now, you might be wondering, if space-time is emergent, what is it emerging from? What's the actual fundamental stuff? And this is where things get honestly speculative, but in a productive way. Several groups of researchers are working on models where the fundamental description is purely quantum mechanical, a system of qubits, or quantum bits, interacting according to some pattern. And space-time geometry arises from the structure of entanglement between those qubits. The idea is sometimes called tensor network models of space-time, and it connects directly to the quantum error correction picture we talked about earlier. Imagine a vast network of quantum systems, each entangled with its neighbors in a specific pattern. The pattern of entanglement defines a kind of geometry. Things that are highly entangled are close to each other. Things that are weakly entangled are far apart. And if you set up the network in just the right way, the emergent geometry looks like a smooth, curved spacetime. Gravity, the force that Einstein described as the curvature of spacetime, arises as a consequence of how the entanglement is organized. This is still a research program, not a finished theory. But the hints are everywhere, and they keep getting stronger. One of the people pushing this forward is Netta Engelhardt, the same physicist who, with Aaron Wall, developed the quantum extremal surface prescription that was so crucial for solving the Page curve. She and others are trying to understand exactly how the emergence works, how you go from a quantum system with no built-in notion of space or time to a world that looks, at large scales, like the smooth, four-dimensional space-time we experience. It's painstaking, technical work, and it's happening right now in the 2020s at universities and institutes around the world. And here's something lovely about all of this. Remember the information paradox? The problem that haunted physics for decades, the question of whether information that falls into a black hole is truly lost. It turns out that the resolution, the Page curve, the replica wormholes, the whole apparatus depends on space-time not being fundamental. The reason Hawking's original calculation gave the wrong answer is that he treated space-time as a fixed, classical background and did quantum mechanics on top of it. But the correct answer requires you to sum over different space-time geometries, including ones with wormholes connecting them, and that sum only makes sense if space-time is part of the quantum description, not the stage on which the quantum description plays out. The information paradox was, in a sense, a clue. It was nature telling us, for 40 years, that our picture of space-time was incomplete, and the resolution points toward a world where space-time is built from quantum information. So where does that leave wormholes? Well, in a funny way, they've come to occupy a position in physics that nobody could have predicted. They started as Einstein's rejected curiosities, bridges that couldn't be crossed, oddities of the mathematics. For decades, they were the province of science fiction writers and a handful of stubborn theorists. But now they sit at the very center of our deepest questions about reality. They're the key to understanding how space-time emerges. They're the geometric face of entanglement. They're the saddle points in the path integral that restore unitarity. They're the theoretical laboratory where quantum gravity becomes almost tangible. And yet, and this is important, we still don't know if a wormhole you could actually travel through exists anywhere in our universe. We don't know if the exotic matter, or the extra dimensions, or the higher curvature corrections that would be needed are actually out there. We may never know, at least not in our lifetimes. But that's okay, because the point of wormholes, the reason they matter so profoundly, isn't really about whether you or I will ever step through one. It's about what they teach us about the nature of reality. They're a window, maybe the best window we have, into the quantum structure of space-time. And there's something almost poetic about that. Einstein, who never fully accepted quantum mechanics, who famously called entanglement spooky action at a distance and spent years trying to show it was incomplete, Einstein gave us the tools, the very equations, that now reveal entanglement and geometry to be two sides of the same coin. The EPR paper, which Einstein wrote to argue against quantum mechanics, and the ER paper, which he wrote about bridges in space-time, published the same year, 1935, turn out to be secretly describing the same physics. ER equals EPR. It took almost 80 years for anyone to see the connection. But it was there all along, hidden in the mathematics, waiting for someone to look at it from the right angle. So as you lie there, maybe drifting off, maybe still half listening, here's what I'd leave you with. The universe, at its deepest level, might not be made of space and time at all. It might be made of something more abstract: quantum information, entanglement, correlations between systems that don't have any built-in notion of here or there or near or far. And from that abstract quantum fabric, space-time weaves itself into existence with all its curvature and geometry and the gravity that holds you gently against your bed right now. The wormholes, those strange tunnels through the fabric, they're not just holes in the weave. They might be showing us how the weaving works. And the people figuring this out, Maldacena in Princeton, Engelhardt at MIT, Suskind at Stanford, all the postdocs and graduate students whose names we don't know yet, they're working on it right now, tonight, probably scribbling equations on whiteboards or staring at laptop screens, chasing the same kind of questions that kept Einstein up at night a century ago. The story isn't finished. It might never be finished. Not completely. But that's the thing about physics, and about engineering, and about any honest attempt to understand the world. The questions don't end. They just get deeper, and stranger, and more beautiful. So let that thought settle over you like a blanket. Space-time, woven from entanglement. Wormholes, stitching the fabric together, information never truly lost, and somewhere out there, in the quiet mathematics of the universe, connections between things that look impossibly far apart, connections that have been there all along, waiting to be understood. That's a good thought to fall asleep to. The universe is deeply, stubbornly coherent, even when it seems chaotic. And the tunnels through it, whether you can walk through them or not, are telling us something true about what it means for anything to be connected to anything else at all. Rest with that. It's a good place to be.